the order of y must be 9. Because whatever its order is divided by 3 is 3. Okay.
I think it's, for example, at big copies of z, for example, we consider z mod 3 plus z mod 3 plus z, for example, as y. So
that won't be an extension of z mod 3 by z mod 3. Because if I take the quotient by one of the copies, I'll have z plus z mod 3.
So we can have more than that.
No. I mean, if I have a group and a subgroup, and I take the cosets, and everything's finite, then I have this kind of relation. And in the example you were trying to give, if I took the quotient by the subgroup z mod 3, I wouldn't get z mod 3 as the quotient. I would get z plus z mod 3. And I always have to, I have these two ends fixed. Okay? So we certainly have the trivial extension. So let's first start by talking about the groups of, abelian groups of order 9. So there are two abelian groups of order 9 up to isomorphism. We have z mod 3 plus z mod 3 and z mod 9. So one of them is cyclic and the other is not. However, we have more than two extensions. So we have at least two extensions. So we have, consider the following extensions. So let's consider extensions of the following form. So let me call this maybe y1, and this is y2. Okay? So if I have an extension where y1 is in the middle, I claim that it's trivial. Okay. So I claim this is trivial. So the only thing that could happen is that maybe there are different ways to split this into a sum, which correspond to different choices of section. So I'm going to leave this as an exercise, because this is taking longer than I expected. So that claim that this is trivial. This is not hard. On the other hand, I claim there are exactly two extensions with y2 in the middle, up to isomorphism. I'll write them down. And the fact that they're exactly two will follow from a general fact, although we could also do it by hand. But what I'll show at least is that there are at least two z mod 3. Namely, so let's write them down and see that they're distinct. So the first one is kind of the obvious one. I could take z mod 9, of course, surjects onto z mod 3 just by reducing modulo 3. So I'm going to take that in both cases as fixed. This is just mod 3. And what's the kernel of that? It's generated by 3. Yes? So I have an inclusion which sends 1 to 3. Like this. Okay. Did I get this correct? GCD of 3. Yeah, I got this correct. On the other hand, I could also send the generator to something else in the kernel. Let's say I sent it to 1. I could have let it go to, say, 6. That's also in the kernel. And I'm supposed to fix these two ends. And are these isomorphic or not? Well, let's see. It looks like they might be. It looks like I can multiply by 2. So maybe I'm supposed to change the quotient. I could, instead of sending 1 to 1, I could send 1 to 2. So let me do that. Let this be not the usual quotient, but let this be 1 goes to 2. And then the kernel's still the same. Right? However, there's no map in here. Is there a map? No, maybe there is. Shoot. Okay. Okay, I think I screwed up this for the moment. Let me give the general statement and we'll return to it and clean it up. Okay, so I claim that for general reasons there should be altogether 3 extensions and we'll classify them in a moment. Okay. Okay, so let's come back to this example. It's possible I got this wrong, that the other two are, there's a non-split extension with y1 in the middle. But altogether, there's going to be 3. Okay, so let me give the construction. I think these are isomorphic, no matter how I do it. So there are only 2 maps, surjections, from Z mod 9 to Z mod 3. One of them sends 1 to 1, and the other sends 1 to 2. Okay. And in either case, it seems to me that I can stick an isomorphism in here making this corner commute.
But then 1 maps not to 3, but to 6.
Which one? If I send 1 to 2, what is the kernel of this map? It's still generated by 3 or 6. They generate the same subgroup. So this subgroup is the same. And if I put in multiplication by 2 here, it preserves this subgroup. The subgroup is 0, 3, 6. And if I multiply by 2, it doesn't, yeah, it preserves it as a subgroup, but it'll go 1 to 1 to 2. Okay, 1 to, yeah, okay, so let's look at it. So suppose I do this 1 to 2 and 1 to 1. If I want this square to commute, I have to multiply by 2, right? Is that right? Does that even work? Then 1 will go to 2, but then 2 will go to 4, which is 1. So that will work. Okay, and that will be an isomorphism because 2 and 9 are coprime. What happens to this subgroup? This is 1 goes to 3. This is what? 1 goes to 3 goes to 6. So I could send 1 to 6.
No, you should do the same here. 1 goes to 3 and then this square will not come.
Yeah, but I'm allowed to choose this inclusion any way I want.
Yes, but we want to find 2 anisomorphic
Okay.
extensions. And if we take 1 goes to 3,
Okay, if I take 1 goes, if this is 1 goes to 3 and 1 goes to 2, that is an extension.
yes,
And this does not commute, although it commutes over here.
yes.
Okay. And once I fixed it like this, there's only one choice here. It has to be multiplication by 2, or could I multiply by something else? So I want to know there's no isomorphism, not just that this particular choice is not an isomorphism. So what else could I multiply by? I could multiply by anything which gives 2 modulo 3. So if I multiply by 4 or 8, what happens? Okay. So indeed, it looks like there's no isomorphism. Okay, so no isomorphism between these two, even though they look very similar. They're not isomorphic as extensions, just as abstract groups, but not as short exact sequences. So this is kind of a subtle point. And, right. So now here's the general phenomenon, so construction. I want to relate isomorphism classes of extensions to X groups. Okay. So given an extension, zero x, y, z. It had to be this, because you can show, if you think of these as vector spaces mod 3, then over a vector space there's always a basis, so you can always split this. Okay, so given an extension like this, apply hom blank x to this sequence to get, what do we get? We'll get a long exact sequence, hom z into x, hom y into x, hom x into x, x1, z into x, and then it will continue. And here there's a special element, namely the identity, yes? So I have 1x, and it maps to something. I'm going to call it alpha. It's just notation. It's whatever the image is here. And now note, we know when an extension is split or not. One way to characterize it was that there was a retraction, that there is a map from y to x that maps to the identity. Okay? So note, the extension splits, so is trivial or splits, if and only if, well, 1 is an image of this, which would be the same as alpha being 0, because this is exact. So this X1 class alpha measures whether or not the sequence splits. Okay? So we say that alpha is the obstruction to splitting the sequence. It's something that gets in the way of trying to construct a splitting. And there are lots of things like this in math. There's some construction you like to do, and there's some cohomology class which obstructs doing it. So you can do it if and only if that cohomology class vanishes. It's usually some kind of trivialization. Okay, so this gives a map from extensions to X1 classes. And moreover, it respects isomorphisms. So moreover, naturality of the long exact sequences for X show that this class alpha doesn't depend, only depends on the sequence up to isomorphism. Alpha depends only on isomorphism class of extension. Okay, so let me formulate the main proposition about this. So there's a map. So the map, we have now constructed a well-defined map from extensions of z by x up to isomorphism to x1. I'm going to be very clear. This is x1 over r. Should have been clear here about that. This is Hom r. If I did it over z, this would be the abstraction to splitting it as a sequence of abelian groups, which is different. Right? There might be a splitting as abelian groups, but not compatible with the action of r. So there's a well-defined map like this. So this map is an isomorphism. And we know that the split extension corresponds to the zero class. So with the split extension, corresponding to the zero class. Okay, so this is a full classification of extensions up to isomorphism. And it's very effective in the case where you can compute this. So in our example here, we could have computed x1 from z mod 3 to z mod 3. By the previous calculation, which I've rubbed off, that would be, just as an abelian group, z mod the GCD of 3 and 3, which is 3. So that would be z mod 3. It's order 3. And we found them explicitly. Okay, so how do we do this? So we'll basically construct the inverse map. We've constructed the map in one direction. I mean isomorphism of short exact sequences of extensions.
I mean the
This is a map, think of this as a map of sets. And then, because this is an abelian group, this at the moment is just a set. And I'm saying there's a bijection of sets. Let me say is a bijection. And then, given that there's a bijection, there must be a way to add these things compatibly with the group structure. That would be the second part. So we'll figure out, given two extensions, what it means to add them. Okay, so proof, we're basically going to construct the inverse. So we're going to check we're going to check that it's surjective and injective. And we'll check it's injective by basically constructing the inverse. So we'll construct a map back, and we'll know it's an inverse once we know that this is surjective. So let's, given, so what we'll do, we need a way to represent the X1 classes. Okay. So fix the beginning of a projective resolution of Z. So fix a short exact sequence. So pick a projective mapping onto Z, and then there's some kernel. And I don't actually care about the whole projective resolution, just the beginning like this. So with P projective. Okay. And now hum into X. What do we get? We get a long exact sequence. Hum Z into X. This is all over R. P into X. K into X. Next term is X1 Z into X. That's what we're trying to understand. The next term would be X1 from P into X. However, that's going to be 0 since P is projective. So if you think of this functor as a contravariant functor, so from the opposite of R modules, then there, in the opposite category, projective becomes injective. And so we're computing this derived functor by humming into injective, and we know that it's exact there. Okay. We'll also give a characterization of projectives like this later. Okay, very good. So I have this. So given any x1 class, I can represent it by a map from K to X. So given any alpha in x1, we can choose a representative let's call it A, and this is just a map from K to X. Okay. So it's just in the image of this map. And it's this A that we'll use to show that there exists an extension producing our given alpha. So what do we do? So now consider the following. Consider K mapping to P, K mapping to X, and now form the push out. So this is Z by construction. This is something. It is what it is. And we're going to show it's actually an isomorphic to Z. So we consider this push out. We get maps of short exact sequences like this. This one, C, by definition, is just the co-kernel of this map. Okay. So I claim that this map Z to C is an isomorphism. So that the bottom row, is an extension of z by x. Moreover, I claim that the corresponding ext1 class is the alpha we started with. So I'll check this in a second. So let me explain why this is the construction we want. So moreover, let's try to compute the extension class of this thing down here. So assuming the claim, let's apply hom length x to get the following. So we'll get long exact sequences. Just a sec. Which will look like the following. So it will be hom. There'll be some kind of incoming terms. There'll be ext1 zx. This will be ext1 zx, everything over R. And by definition of the extension class, it's the image of the identity under this map. Yes? So this is 1x, it goes to alpha. On the other hand, this diagram commutes. And 1x here maps to this element A that we started with. And A, by construction, we chose it to be a lift of alpha. Okay. Sorry, this is the extension class. Whatever it is, we don't know yet that it's alpha. But this one, by construction, is alpha, and they're equal. Okay, so the extension class actually equals alpha. So as soon as we know that the co-kernel really is Z, then we've provided an extension whose extension class is alpha. And therefore, this map is surjective. And if you don't mind, I'll go 5 more minutes since I started a little late, if no one's going to come and kick us out. Is that okay? I think I'm already over time. I want to at least finish this proof. Okay. Right. So that gives surjectivity of the map. We need to check that Z to C is an isomorphism. So, so what? So you can check so you can consider the snake lemma for this map of short exact sequences. Snake lemma applied to this map of short exact sequences. Maybe even a better thing to do. You could do this. The other thing we could have done is just put Z here and computed the kernel of this map and showed that it's actually equal to X. Right. Mm-hmm. Let me say it like this, though. So let me tell you what you have to check. So if I consider the snake lemma applied to this map of short exact sequences, you can check that the kernel of this map and of this map are the same. So this is an elementary check. So the kernel of the two of the left and central vertical maps are identified. And what? And so the kernel of the map from Z to C will be 0. No. I don't know that yet. That will be true. And the map on cokernels, and similarly for cokernels. Okay. So we're over time. I'm going to make this into an exercise for the seminar today. We'll do it in detail. It's just checking what the elements do. Okay. So from the snake lemma, we'll see that these two terms are isomorphic on the cokernels, these two terms on the kernels, and therefore this will be an isomorphism. And so this gives the surjection. Let me tell you the kind of inverse process. So we need to know that every extension is of this form, up to isomorphism. So, so conversely, we claim every extension is of this form up to isomorphism. So we have an inverse map. And the way this goes is the following. So given an extension 0, x, y, z, by projectivity of P, we can lift the map from P to Z to a map from P to Y. So we can construct a map of short exact sequences. So we have the given extension. This is P, this is Z. I'm going to just let this equal Z. Then whatever the kernel is, it must, since this commutes, it must map into the kernel here. And this map is just given by lifting along this surjection. Okay? And so by the universal property of the push-out, since this square commutes, we'll get a map from the push-out, x plus p over k, under k, to y. And you need to check it's an isomorphism. And again, this is going to be something very explicit with elements. Okay, so we'll do this in the seminar. We'll do one more thing in the seminar also, which is how to add extensions. Okay, so let me say that. So see seminar sheet. I'll add this for the record. See seminar sheet for how to add extensions. So this is called the Baer sum. Baer, I think, must have been German. Okay, so we'll stop there. Any more questions? We'll give more details in the seminar of the proof. We ran out of time.